So let us now see how they actually work. What actually happens when we have a database crash? What do we mean by crash? Instance failure, power cut, shutdown abort, Aura 600 crashes the database. Someone pulls the power supply, the plug out the back of the computer, whatever it is. Instance crash. We then have to restart the machine, restart the database, and Oracle is thrown into the crash recovery process. And that's what I want us to understand, the internals of what actually happens following a crash. So let us say we issue some simple DML statement. Here I am, logged on as user Scott. Oops, show user, I'm logged on as Scott. And I'm going to issue this command, update emp set sal equal 1500, where ename equals Miller. We'll begin by seeing what is in memory and what is on disk. First off, simple query here. We have to do some work within the data dictionary here to understand what's happening. But this query here, select object name, data object ID from DBA Objects, where object type equals table and owner equals Scott. The data object ID identifies the segment on disk where the object resides. And it looks from this query as though Scott owns 4 table objects. And each table object has a data object ID. Now, another view, $BH. There are quite a few views kicking around we can use to run these sort of queries, but $BH is the one I'm most used to at this point. $BH, in principle, will give you one row for every block that is in memory, every block that's in the database buffer cache. Every block is identified as being a certain number, a block number and a file number. So blocks and data files are consecutively numbered. Now, every block is also part of a data object. And there's the column OBJD, and that's your join column back to data object ID in DBA Objects. Why isn't the column the same name? Ask Uncle Oracle. So the Scott.emp table is object ID 81262. Is any of that in memory at the moment? Let us see by querying $BH. Select file hash block hash status dirty from $BH, where OBJD equals 81262. So that's how I join back to this view to pick up the emp table. No rows selected. Not one block of Scott.emp is in memory right now. I'll query it. Select star from Scott.emp. That will be a full table scan from Scott.emp. Back come the rows. Now rerun this query. There appear to be 7 blocks that make up that table. They're all in file 7. They're all in file 7. They're all there. And they are now in memory. Now that one is a dirty block. It's been updated at some point. The other blocks are clean. They have not been updated for any reason, but that's been updated at some point in memory. I'll just clean the memory with alter system checkpoint. That will copy all dirty buffers to disk. And now none of them are dirty, they're all clean. So I've got a clean copy of the table in memory. Now, and that was brought into memory when I scanned the table with that statement there. I'll do my update. Update emp set sal equal 1500, where ename equals Miller. I'm not really concerned about execution plans at this point, but I'm sure you will all be aware, those of you who are interested in SQL tuning, this is going to be a full table scan to pick the row and then do the update. So I've done my update. Coming back to my graphic here, what's happened? I issued the statement. My session server process goes to the buffer cache to say, is the block you want to write to in memory already? The block containing Mr. Miller's row, is it in memory already? If it is, great. But it actually is, because I just scanned the table. What if it weren't? If it weren't, my server process will go to the data file, find the block, copy it into memory. So we copy into memory the block containing Miller's row, and of course his salary is 1,300. We copy that block into memory if it isn't there already. That's how the buffer cache is populated. Session server processes read data files into memory. The statement I just executed was a DML statement, an update. Every update is protected by undo and redo. The undo has the pre-update version of the data, which is written or stored in an undo segment. So we've got to get a spare or available block of undo. Okay. Copy a block of undo into memory. If it isn't there already. If it isn't there already, disk read. Otherwise, maybe there's an available block in memory as it is. So I've now got my table block in the cache, my undo block in the cache. We are now in a state where we can proceed with the update. Now, when we do DML, to make the change, the server process writes the change vector to the log buffer. That's the first step. We write the change vector to the log buffer. There will be two changes here. We're going to write the new value of the salary to the data block. We're going to write the old version to the undo block. So that's two change records or change vectors. A change to be applied to the table, a change to be applied to the undo. We place those changes in the log buffer. The log writer process in near real time will flush that log buffer to disk, to the online redo logs. That's going to happen in nearly real time. Worst possible case is a 3-second delay.
Hey, John, pardon me. So question for you. Over the years, it seems like the flushing of the redo log from from memory to disk has had almost a very numerous amount of architecture changes. So maybe, it's not possible to go into the complexity of when it flushes the redo log buffer to the redo log disk. But is there any light you can shed on that?
Yes, there is. It happens in very near real time, but the vital point is when you issue a commit, it is real time.
So if a commit is this, would the return from a commit mean that it is successfully written to disk?
Yes, it will. When you issue a commit statement, your session hangs while the log buffer is written to disk, and only when that write is complete is the commit complete record returned to your session, and that's the durability. Oracle's guarantee of durability is that the change vectors needed to repeat the change are on disk.
Thank you.
That's an important point. So it happens in near real time, and when you say commit, it is real time. So I've now done my update. A few seconds have gone by. Those change vectors will be in there, but we also, of course, have to actually update the data block itself. We copy the old version of the data to the undo block, which is the change vector applied to undo. Then we make the change to the data block. And the transaction is now not complete. The update statement is now completed. I've changed the data block of the table. I've written the old version to the undo block. I've got change vectors for both changes in the redo stream. What's in the data files? Quite possibly nothing at all. Now, we can run a few more views to see what's going on at this point. Run a few more queries. We have $transaction. $transaction will have one row for every active transaction. Each transaction will have been started at a particular time. Its undo will be in a particular undo segment, identified by XID USN, undo segment number, transaction ID, undo segment number. And there are other things you can see, how much undo the actual session has generated so far. And one very simple query here is to see how big my transaction is at the moment. And in my entire database, there's one transaction. It's being protected by segment number 5. It started then. It's using one block of undo, one undo record for the 2 writes. And the transaction's in progress at this precise moment.
John, can $BH, data dictionary view, be used to tune redo? And what's, if there is, what's a corresponding view in the AWR repository?
You can't do much tuning with this at all. It's merely informative. What you can see, though, is fascinating. Look at this. At this point, I've queried the table. I've done a checkpoint, which flushes all dirty buffers to disk. And we see that object ID 81262, there were 7 blocks of it, all those blocks of it in memory. None of them are dirty. Now I've done an update, though. Having done the update, run that query again, there's a dirty block. Block 150 of file 7 is the block that contains Mr. Miller's row. And that's the proof of it. It's been updated. It is dirty. Uncommitted transaction note. Uncommitted transaction. And it hasn't been written to disk. If I were to alter system checkpoints, that forces Oracle to write all dirty buffers to disk, to the data files. And the block is now no longer dirty. It's been written to disk, it's clean. There's the old version, a consistent read version. So, what if we then do a commit? At the moment, nothing's gone, well, because I forced a checkpoint, things have gone to the data files, but otherwise nothing's on the data files. I'll issue a commit. We put the commit record in the log buffer, and as just discussed, my session now hangs while the log buffer is written to disk. And only when that write has happened is the commit complete recorded. So if I do a commit right now, my session hangs for a fraction of a second while the commit is done. Now, point to remember at this point, as I mentioned earlier, the log writer writes a very aggressive algorithm, very nearly real time. And when you say commit, it is real time. The writing of redo to disk is the ultimate bottleneck in the Oracle system. You cannot commit transactions faster than the log writer can stream those changes to disk. So that was a straightforward committed transaction. Now, the committed transaction then just means you've updated things in memory, all the change vectors are guaranteed to be on disk. What about the writing to the data files? Well, I've got these 2 change blocks in buffer cache. The change that was applied to the table block, the change that was applied to the undo block. When do they get written to disk? For the purpose of demonstration, I forced the write by using the checkpoint command. That forces database writer to write all dirty buffers to disk. Under normal circumstances, you would never issue an alter system checkpoint. It cripples performance. So I've got my 2 change blocks in buffer cache, but my redo records are on disk. My database at this point is corrupted. It is missing a committed transaction. That's a corrupted database. It's missing a committed transaction. If the database crashed right now, that transaction would be gone because it never went to the data files. But we'll see how the crash recovery will reinstate it. Let's take the example, make it a bit further, a bit more complicated. Another user does something. He says update dept set lock equal to Paris, where dept now equals 20. So update a totally different table, perhaps. Now, the department 20 is previously, by the way, the location is Dallas, if I remember correctly. So we do that update. What happens? My server process copies blocks into memory, copies the block of data file up into memory. There it is. Location is Dallas. We copy a block of undo into memory. Then we repeat the process, generate the change records, which will go to the redo stream in pretty much real time. Then we can do the changes. Copy that to the undo block, update the table to Paris. So uncommitted transaction at this point, done in my other session. Now, what happens next? Fred maybe doesn't issue a commit. He goes off to lunch. But Scott's block up here perhaps is repeatedly being used for some reason or other. Database writer, the algorithm database writer uses to determine when to copy blocks to disk, is not related to commit processing at all. Scott's update was committed. Okay. Database writer will not write it to disk, though, if people are continually looking at the data. Why write it to disk if people are accessing it in memory all the time? On the other hand, in my rather trivial example, Fred did his update, which he hasn't committed, and maybe no one looks at those blocks again. They're idle blocks. What does database writer do then? Database writer starts to search the buffer cache for changed blocks which are no longer active. Database writer will only write a block to disk if it is firstly changed or dirty, because there's no point in writing a block that hasn't been changed, and also will only write a block that is inactive, because you don't want to write a block that's continually being accessed. So the algorithm is not related to commit processing. So in my example here, we assume that these committed change but continually being accessed, these are uncommitted change, but nobody's interested in the data. So database writer is more than likely going to copy these to disk. Now we have a particularly important point. When database writer writes a block to disk, it writes a block written record to the redo stream. So database writer copies blocks to disk and writes to the redo stream the addresses of the blocks it's written. That's an important change for performance of recovery. It writes to the redo stream the blocks, the addresses of the blocks that have gone to disk. So the redo stream knows all the changes, and it also knows which of the blocks have been checkpointed to the data files. And at this point, my database is unbelievably corrupted. It is missing the first committed transaction, but it is storing the uncommitted transaction. That's a corrupted database. Uncommitted data is in the data files. Committed data is not in the data files. Does that matter? No, because in memory, everything is fine. In memory, Oracle knows that's not committed and that is. But the data files are now seriously out of date. What happens next? Well, our problem is the database writer writes in a lazy algorithm. And there is no correlation between database writer writing and commits. SQL Server, for instance, is completely different here. As I understand it, SQL Server, when you commit, writes the entire transaction to the data files. Oracle doesn't. It just writes the change vectors to redo log, which of course is far, far faster. That's why you can commit a transaction that updates 1 million rows and takes half an hour. You can commit in a fraction of a second. So database writer is always writing behind.
John,
then we have a disaster. Yes.
John, what table or view was used to find out what file or block a table belonged to?
It was the query I ran. Well, if we look at DBA Objects, there are several ways to creep up on that question. DBA Objects does show for each object and object types that are data objects, such as indexes or tables or partitions. A data object, each have an object type, will have a data object ID, and that's the pointer that will show you where it is on disk. That will show you which files it's actually in, because that we can use as a join column to several directions. We can use that as a join column to $BH to see, and there's the join column there, to see where the object is in memory. But we can also go from DBA Objects to DBA Segments. And DBA Segments will then give us an idea for each segment has a name and an owner. I'm going to tie that back to DBA Objects for object name and owner to see the detail of which table space it's in and the header block of the header file, well, the header block basically of where the segment actually is. Was that the question, or have I gone off in the wrong direction?
I think you did it. Thank you.
Thank you. Right. So Oracle now crashes in my example. And at this point in my example on the slide, my committed transaction is only in memory. My uncommitted transaction is on disk. Note I haven't committed that. And looking at going back to my views, unless database writer has caught up, yep, there is a dirty buffer, a dirty block in memory. It's the same block. It's such a small table that both my rows are in the same block. But that update wrote to that buffer, that block in memory. It hasn't been written to disk. Well, if it had been written to disk, I'll just do it. I'll do a checkpoint. Hold the system checkpoint and force a write to disk. See how lazy database writer is? It still hasn't written that to disk. No need to. Right. Now my uncommitted transaction hasn't gone yet. This view doesn't get updated necessarily in real time. $$ views are never transactionally consistent, so it may take a while before that gets updated. But the checkpoint will have written everything to the data files. Now let us assume then we have the crash. What happens on startup? Right. Crash recovery, because at this point my database is corrupted. It's missing a committed transaction, it's storing an uncommitted one. So crash recovery is going to rebuild the SGA to the state it was in before the crash. So then it will roll back the uncommitted work. So it's two phases. Forward recovery, we reinstantiate all the work that wasn't written to disk, which will include uncommitted work. That then has to be rolled back. So I'll crash the database with shutdown, abort. So it's cut the ground out from beneath Oracle, terminate the database, the instance. That's a crash. Let's take a look at the trace files, the logs. Oops. Just see the alert log so we can see what happens. So terminating the instance. Goodbye. Now we try a startup. Right, all sorts of things going on. As we can see, the message is written out to the alert log. Database is mounted. Database is open. Well, let us drill through this and see what actually happened there. Oops. BI, the alert log. Oops. Right. So look at, that was a bit too quick, it scanned through there. We'll see what happened when I did the startup. And we'll see the crash recovery, what actually happened in the alert log, and then we'll go through the theory. So my startup command, there's the shutdown, terminated with my abort. Then we have the startup. Now, parameters used to build it, start the background processes. That should get us to no mount mode. Then we mount the database. We attempt to locate and read the control file. Okay, successfully mounted. Completed auto database mount. But now, beginning crash recovery, Oracle realizes that it was a crash. Nothing was flushed to disk. So it scans the redo log. It scans the redo log. And Oracle has worked out that there's 23 kilobytes of redo, 33 blocks need recovery. Right. It's actually a two-phase process. So looking at it on the graphic, Oracle scans through the redo log, looking for the block written records. Every block written record that it finds, it knows that block was safely on disk at the time the instance crashed. It doesn't have to do anything for that block. But all the change vectors that apply to blocks for which there's no block written record, those have to be recovered. And that's what they call the crash recovery. So it's scanned through the redo log, working out which blocks need recovery. Those are the blocks that were dirty at the time of the crash. In my example, the committed transaction. So we start the redo application. How does that work?
John?
Right. We could, yes.
Pardon me? Yeah, I'm sorry. Do you have to set a parameter or start a process in order for crash recovery to start?
Absolutely not. You can't stop it, even if you wanted to. Quite straightforwardly, if the crash recovery fails for any reason, Oracle will never let you open the database again. It's that straightforward. That's what I mean when I say you'll never have a corrupted Oracle database. The crash recovery will always start automatically, repairing the damage, and if it fails, it's goodbye database. But it should never fail if the DBA knows what he's doing. So it's totally automatic. So we scan through the redo log, finding the change vectors that apply to blocks that were dirty at the time of the crash. Right, we can ignore the ones that have been checkpointed already. We've got to rebuild the SGA to the state it was in before the crash. So we find a change vector, the Scott's table block. Copy the block into memory from the data files, apply the change. The next change vector was the undo one. Changes to undo segments generate change vectors as well. So there's Scott's undo record. Copy the undo block into memory, apply the change. Then we find a commit record for Scott. So we flag the record, the transaction, as committed. What's the next change vector? Well, it would have been the change record for Fred's table, Fred's transaction. However, that one was written to disk as a dirty buffer, uncommitted, which we know about because of the block written record. But then we do maybe find the change vector for Fred's undo record. Copy that into memory, apply the change. So we've now reinstantiated the committed transaction that wasn't on disk, and we've also reinstantiated the undo needed to roll back the uncommitted transaction. And we've run out of redo. And there's no commit record for Fred's updates to the depth table. So the SGA is now in the state it was in before the crash. We've reinstated both the committed transaction and the undo needed to reverse the uncommitted transaction. At that point, we can roll back the uncommitted work. And that happens completely automatically. Going back to my alert log here, we've done the recovery, we've applied the redo, completed it. A few more bits and pieces go on, but very interestingly indeed, we then open the database. I forget exactly what release that came in, and I think it was release 7.3. It's a long time ago, I think 7.3. From release 7 point whatever it was, the rollback of the uncommitted work actually occurs after opening the database. You open the database and then do the rollback. There's no reason not to, because the rollback might take a long time. So why not open the database before you do it? If, through bad luck, someone tries to get us a block that needs to be rolled back and hasn't been, not a problem. The rollback will be done on demand. So that's the crash recovery process. It is, I believe, totally impossible to break. The mechanism of undo and redo, where all changes written to the data files are protected with change vectors written to the redo log, means it is always going to be possible to reinstate committed work that was not in the data files and to back out uncommitted work that was written to the data files. So you can't ever corrupt your Oracle database as long as one does not happen. What is that one thing that could cause this mechanism to fail? What if, as well as crashing the instance?
All right, we've got some answers coming in. Good. Excellent. Keep them coming, folks. We've got a lot of good answers coming in. but we've only got about 10% of the people, or whatever it is. More answers. Under what circumstances would Oracle crash recovery not work? What did we need? Good answers coming in.
Okay. Shall I give him the answer?
Go for it.
Redo. The redo log. Some people refer to the redo log as being the Achilles heel of the Oracle database. That crash recovery mechanism requires those change vectors in the redo log. If the redo log is damaged as part of the crash, no reason why it should be, but if something absolutely awful happens to your hardware, and you not only lose the instance, but you damage the redo log, that recovery is impossible. So, how do you protect the redo log? Next question, people.
Yeah, I would also offer, there was the suggestion that data files not existing would prevent crash recovery from happening. Yeah, that's true. Technically, doesn't hit the heart of the problem, though. So I lean towards having the online redo log file or files available.
That's the one. That's the one. As long as the online redo log files are available, the DBA should be able, well, the instance should recover itself. If the redo files are not available, you can never open the database again. You are forced to do incomplete recovery up to the last log switch, assuming you're on archive log mode, or complete recovery from your last incomplete recovery from your last cold backup if you're not in archive log mode. So you must have that online log.
I'm terribly sorry, John. By the way, all of this is covered with workshops managing, configuring redo logs, archive logs in the admin level 1 class. Back to you, John. You were asking a question.
That leads us up. Yep. What do we do to protect the online log? There are 2 possible answers to this, I would think. Quite straightforwardly, look at how the online log here is configured.
Watch it.
Oops, thank you. Right. Right. My online log, that was just querying VDOL log, consists of 3 groups, group 1, group 2, group 3. That's the vital column. Each online log group has 2 members. So to conclude then, the mechanism of crash recovery is absolutely impossible to avoid. Even if you wanted to, you can't. Oracle will do it automatically. The only issue is if your online log is damaged. And for that reason, you protect it. Historically, always with multiplexing to at least 2 members for each group. Though nowadays, with the Oracle engineered devices, Oracle is using ASM mirroring to protect it instead.
Do you recommend ASM mirroring, John? Or do you recommend ASM?
I certainly do. ASM adds a layer of complexity to the Oracle administration, but the benefits you get in terms of performance and reliability are huge. And also, if you're using Oracle engineered systems, ODA or Exadata, it can be pretty cost effective too. Yeah, so ASM, preferably on engineered systems, go for it. And it gives you very nice fault tolerance to the redo log too. So that concludes my exposition of crash recovery. What I've tried to go through is give you the detail of how the mechanisms of undo and redo mean that no matter what is happening at the time of a crash, it will always be possible to reinstate all committed work and roll back all uncommitted work. No matter what you do, you cannot corrupt an Oracle database.